Hi, welcome back. We've talked about intermolecular forces. The last couple of videos have been about intermolecular forces. Now we're going to move on to applying intermolecular forces to actual chemistry, right? There's two problems that we're really going to look at and relate back to intermolecular forces. And the first one is going to be phase changes. That's what this video is about. So melting, evaporation, freezing, that kind of stuff. Like what changes when we change states of matter as far as intermolecular forces go. And then the second one is going to be um, solutions. And so what happens when we dissolve a solid in a liquid or a gas in a liquid or whatever, some substance being dissolved in another, what's going on with those intermolecular forces? So that'll be the next set of videos, right? So this one's phase changes, and then we're going to solutions. So as far as phase changes go, remember that when we talk about gases, liquids, and solids, gases are very fast molecules that are not interacting with each other, right? And so gas molecules bounce off each other. There are no intermolecular forces there. They're not strong enough to hold molecules together. Liquids have a little bit more intermolecular forces. They can kind of keep molecules in the same vicinity, but obviously liquids have a lot more freedom of movement than solids. Solids have no freedom of movement. A lot of molecules are bound very tightly, and the intermolecular forces are the things that do that. And so, thinking about that, I think it starts to become a little bit clear how intermolecular forces are part of these phase changes. So we're going to go back to water. Water is the easiest one to use for examples like this. So water goes from ice as a solid to water, liquid water as a liquid, and then water vapor as a vapor. So when we look at what happens chemically in this, so there's a couple of things that I want you to see once I switch over to the slide. One is look for those intermolecular forces, right? Dipoles are lining up, interactions are happening between the partial positives and the partial negatives. And the other thing that I want you to notice is the covalent bonds. Remember that covalent bonds are much stronger than um, intermolecular forces, dipole-dipole interactions, or even hydrogen bonding. And so those covalent bonds are much stronger. And so when we add heat to things that have intermolecular forces, the first thing that's going to break is going to be those dipole-dipole interactions or those hydrogen bonds. And that's what we see right here, right? We have ice over here. Ice is just a whole bunch of water molecules that have very strong attractive interactions between hydrogen bonding dipoles. So we have a delta minus on the oxygen because oxygen is very electronegative. We have a delta plus on the hydrogen because hydrogen is not very electronegative. And when those water molecules associate with each other, when the temperature is low enough that these molecules slow down and end up being close to each other, they all connect like this and they all attract each other, and there's this nice strong lattice of hydrogen bonds that holds everything in place, right? And so that's what makes ice. And then as we heat it up, of course, what's going to happen is we're going to impart more energy. Heat is just energy. Anytime we say we're adding heat, we're adding energy to a system, and that energy is going to make these water molecules move around a little bit more, right? It's going to give them more velocity and more kinetic energy. And what that means is that eventually the connections, the attractive forces that are holding these things together are going to start to break down. There's going to be more energy in this water molecule than there is attractive force between this delta plus and delta minus. And when that happens, this hydrogen kind of separates away from the oxygen. Right? So in liquid water, there's still hydrogen bonding. We still have connections between hydrogens and oxygens. Right? You can still imagine delta minuses and delta pluses and dipoles and all that kind of stuff in there, but there's less of it, right? And so there's less of these hydrogen bonding connections, and what that means is that these water molecules have a little bit more freedom. They're not held as tightly by these attractive dipole-dipole forces. Right? Add more heat, and of course, the intermolecular forces start to be overcome even more. Notice that all our covalent bonds are still in place. We're not breaking off any hydrogens away from the water. We're not breaking any hydrogen-oxygen bonds. All we're doing is we are separating these dipoles from each other. And when we have water vapor, these water molecules are moving so fast but now they can't attract each other, right? The water molecules have so much kinetic energy that even though this oxygen has a delta minus on it and this hydrogen has a delta plus on it, they're moving too fast to ever get that um, give that attractive force time to kind of hold those molecules in the same place. So as we add heat, we go through these phase changes and what's happening there. anytime, not just water. This is any chemical compound. As you heat it up, as you melt it, as you evaporate it, what you're doing is you're creating more kinetic energy for those molecules, and that kinetic energy slowly becomes greater than the attractive intermolecular force, and those molecules start to separate. And they start to move around faster, and that means that you have fewer intermolecular forces, right? And so that's the solid, liquid, gas hierarchy that we've been talking about over the last couple of videos. All right, so the next set of videos is going to be about solutions, and that should finish up week 1. Hopefully those are coming soon. And then in week 2, we'll talk about solutions pretty much nonstop. So we're going to get the theory of solutions and relate it to intermolecular forces, and then we're going to do some calculations with solutions after that. All right, I'll see you in the next one.